There you see we're talking about absolute and conditional convergence. And we do that at the end of discussing all of the different tests. The first thing we have to be aware of here, let's kind of get first things out of the way. If the sum of the absolute value of terms converges, then the sum of the terms without absolute values also has to converge. After all, this is a sum of all positive values. This is a sum of things that might be positive and negative, and certainly this is going to be smaller than this. Okay, and so because some of these might be negative, so since this series is smaller than this and this one converges, then our original series also has to converge. Well, we've so and we've discussed this before, as I mentioned earlier when we talked about the test for the ratio test and the root test. We talked about absolutely convergent. So a series is absolutely convergent if the series of the absolute values converges. Okay, so it's absolutely convergent if the sum of absolute values converges, and we already know if the sum of absolute values converges, then the original series converges. So this is kind of a stronger statement than just regular convergence. If it converges absolutely, it really converges, if you will. Okay. Now, conditionally convergent, a series is conditionally convergent if it converges, if the original series converges, but the sum of the absolute values does not converge, it diverges. So that's conditionally convergent. It's what is less strong, if you will. Well, let's look at an example here. Consider the series from n equal 1 to infinity of negative 1 to the power n plus 1 over n. It's an alternating series, by the way, and we've already seen that this alternating series converges. We've seen that when we started looking at the alternating series test. So we know the series converges. So that now the question is, does it converge absolutely? If it converges and converges absolutely, we say it's absolutely convergent. If it converges, but the sum of the absolute values does not, if it doesn't converge absolutely, then it's conditionally convergent. Now, the sum of the absolute values, all we're doing is making everything positive, and so that's just the sum of 1 over n's, which is the harmonic series where p is 1. That's the p series where p is 1, and that diverges. So since the series converges, but the series of the absolute values diverges, then the series is said to be conditionally convergent. Okay, well, let's look at some more examples. We want to know whether this series is absolutely or conditionally convergent. So what we first have to determine is if it converges itself. Then we'll worry about whether it converges absolutely. So we look at the series now. What might we try on this series? Well, it looks like maybe we should try the alternating series test because it certainly is alternating. And now here the a sub n's are just this piece of it, not the entire series, not the entire term of the series. It's just this part of it. And of course that's positive. And what I started to do here is try to decide whether these were getting smaller by comparing a sub n plus 1 to a sub n, and that looked kind of messy, so I stopped. So what I'm going to do is what we've done in the past is I'm going to create a function f of x, which is x over x squared plus 1, which is parallels this part of the series, the a sub n. And when I looked at its derivative, I got 1 minus x squared over x squared plus 1 squared. And for x is 1 and greater, of course, the denominator is always positive, and the numerator would be 0 when x is 1, and when x is 2, it would be negative, wouldn't it? So this is going to be less than or equal to 0 for all x is greater than or equal to 1, which means the function is decreasing whenever x is greater than or equal to 1, which means a sub n over n plus 1, n squared plus 1 is getting smaller as n gets larger. And so that's the idea, that the a sub n's are decreasing based on that information. Now, the limit of the a sub n's, in a nutshell, we're taking the limit of n over n squared plus 1, and without a whole lot of work, we can figure that's equal to 0. And so, yes, because now the alternating series test tells us our original series converges. Okay, that series converges. So now the question is, does the series of absolute values converge? Oops, and that's a -1 with a power on, and I see I left that power off. But now our question is to decide whether it's conditionally or absolutely convergent. So to decide whether it's absolutely convergent, we look at the series of the absolute values. And of course, the series of those absolute values is just because of the negativeness of the terms. When we take absolute value, we're going to make sure all terms are positive, which will give us this. Now, to decide whether this series converges, then we would have to use some other test, because it's not an alternating series now, is it? So we've got to use some kind of test, and I'm using the limit comparison test, which is, if you recall, is we're going to choose our series. Okay, we're going to choose our series to compare to. We're going to compare this to another series. And we're going to compare to this. Remember, the limit comparison test says, okay, what we're going to do is take the highest power of n in the numerator and the highest power of n in the denominator, and this is the way we decided to choose the comparison series. And ignore all other parts. Well, that gives us the sum of n over n squared, which just simplifies to the sum of 1 over n. Now, we know that diverges, okay? And so what we do then is that we, remember the way this limit comparison test works, we look at the limit of our series a sub n, in terms of our series divided by the terms of the comparison series. And our terms are n over n squared plus 1, and the comparison series, the terms are 1 over n. And when we simplify that ratio, we get n squared over n squared plus 1. And so we find the limit of this ratio is n squared plus 1. Okay. And because that is 1, then we know it's positive and finite. That's the issue. So we know, and we know that the series of b sub n diverges. Remember, they either both diverge or both converge if the limit of that ratio is positive and finite. And so that tells us our series diverges. Now, you're probably going to have to go back and review how you use the limit comparison test, but that's what we've done, and I've given it in a nutshell here. So here's where we are. The original series converges, but the series of absolute values does not converge, so the original series is said to be conditionally convergent. So sometimes it's a tough job to figure out whether it's absolutely convergent or not. Let's see what else we've got here. Okay, let's consider this series. Here we have a series that 2/3 plus 2/3 squared minus 2/3 cubed minus 2/3 to the 4th power plus plus minus minus plus plus. Not an alternating series. We want to know if it converges or diverges, but it's not an alternating series, so we can't apply that test. So here's what we could do. This is kind of clever. So let's look at the absolute value of the terms. Okay. Now the absolute value of the terms, if we look at that series, then that's actually a geometric series, and it converges because r is 2/3, which is less than 1. Okay. So the series of absolute values converges, so the series is absolutely convergent, which implies also its convergence. So we took a completely different path on this one, much different than anything we've done before, because we went directly to trying to find out whether it was absolutely convergent, which implies convergence as well. Okay, in this example here, again, we happen to have an alternating series, and we want to know whether this is absolutely or conditionally convergent. Well, from the alternating series test, we can figure out real quickly that this converges. So the next thing we have to do is decide whether it converges absolutely. And so when we look at the sum of the absolute values, we just have the sum of 1 over n squared plus 1. Now we're going to use this as the direct comparison test, and we're going to compare this series that we're looking for to a p-series, okay? And since each of these terms is smaller than these, because each of these denominators is bigger than these, okay, so we know this series is smaller than this series, its sum. And this is a p-series where p is equal to 2, and we know that converges. So if this converges, then a series that has a smaller sum must also converge. And so the series of absolute values converges, and that's all I'm saying here, is the direct comparison test, the larger series converges, so the smaller one does. So that tells us that our series is absolutely convergent. Remember, you can pause and go back and so on through all these, and sometimes I would certainly need to if I were you. Well, that's the end of our discussion on absolute and conditional convergence. Put it to good use, please.